Welcome. This video will cover the architecture of database systems. We'll explore the essential components and structures that make up these systems, providing a foundational understanding of how databases are designed and function. A database system is essentially an organized collection of data. This data is stored and accessed electronically, making it efficient to store, retrieve, and manage. The database system provides an interface between the data and the applications that use it. Some of the key characteristics include data persistence and durability, which means that the data remains intact even through system failures. Concurrent access by multiple users is another critical feature. Database systems maintain data integrity and consistency, ensuring reliability. They also offer security and access control to protect sensitive information, and they are designed for scalability and performance, accommodating growing data needs. The three-tier database architecture is a common design pattern for database systems. It consists of 4 layers. At the top is the presentation layer, which is essentially the user interface. This is what the users interact with directly. The second layer is the application layer, which contains the business logic. This layer processes user requests and coordinates with the data access layer. The third layer is the data access layer, which provides the interface to the database management system. It handles the actual interaction with the database. And finally, we have the database layer, which is the physical storage where the data resides. A database management system consists of several core components that work together to manage data. The storage manager handles data storage, retrieval, and updates on the disk. The buffer manager manages the transfer of data between the disk and the main memory. The file manager organizes database files and manages disk space allocation. The query processor parses, validates, and optimizes database queries. The transaction manager ensures that database transactions adhere to ACID properties, which are atomicity, consistency, isolation, and durability. Finally, the recovery manager handles database recovery after system failures. The query processing pipeline is the sequence of steps a database system takes to execute a query. First, the query parser analyzes the SQL queries and translates them into an internal representation. It also validates the syntax and semantics of the query. Next, the query optimizer generates the efficient execution plans by evaluating multiple execution strategies. Finally, the execution engine executes the optimized query plan and returns the results to the user. Database storage architecture involves different levels of abstraction and various structures to efficiently manage data. The storage hierarchy includes the external schema, which represents user-specific views of the database, the conceptual schema, which defines the logical structure of the entire database, the internal schema, which describes the physical implementation details, and physical storage, which refers to the actual data files, indexes, and storage structures. Some common storage structures include files, which are collections of records, pages, which are fixed-size blocks, records, which are collections of fields, indexes like B-trees and hash indexes, table spaces, which are logical storage units, buffer pools, which are memory caches, and write-ahead logging. Transaction management is critical for maintaining data integrity and consistency in a database system. This is achieved through ACID properties. Atomicity means that all operations in a transaction either succeed completely or are entirely rolled back, ensuring that transactions are treated as a single indivisible unit. Consistency ensures that a transaction brings the database from one valid state to another, maintaining all defined rules and constraints. Isolation ensures that concurrent transactions execute as if they were running sequentially, preventing interference between them. And durability ensures that once a transaction is committed, its changes persist even in the event of system failures or crashes. Concurrency control is essential to manage simultaneous access to a database by multiple users. Without it, problems like lost update, dirty read, non-repeatable read, and phantom read can occur. The isolation levels are used to control the degree to which concurrent transactions are isolated from each other. These levels include read uncommitted, which allows dirty reads, read committed, which prevents dirty reads but allows non-repeatable reads, repeatable read, which prevents dirty and non-repeatable reads but allows phantom reads, and serializable, which is the highest isolation level and prevents all concurrency issues. Isolation levels can be set using SQL commands such as set transaction isolation level serializable. In summary, we have covered several key components and concepts of database architecture. The three-tier architecture with its presentation, application, and database layers is a fundamental design pattern. Core components such as the storage manager, buffer manager, query processor, transaction manager, and recovery manager are essential for DBMS functionality. The storage hierarchy with its external, conceptual, internal, and physical layers provides different views of data. Transaction management, including ACID properties and concurrency control, ensures data integrity. As for future trends in database architecture, we anticipate increased adoption of cloud-native databases, greater integration of artificial intelligence for self-tuning and intelligent query optimization, and wider use of in-memory processing for ultra-fast data access and real-time analytics. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.